Okay, time now for another video presentation. This one is on two-dimensional motion. Up until now, we've been talking about motion in one dimension, basically in a straight line, and now we're going to talk about two-dimensional motion, like the snowboarder in the picture here. Alright, so a certain kind of two-dimensional motion is called projectile motion. We spend a lot of time talking about projectile motion. And a projectile is something that is flying through the air and only gravity is acting on it. So we could give examples, of course, of projectiles and what some of those might be. Okay, and yeah, come up with some and we can talk about them in class. Okay, and here's another thing that we could talk about in class too, and that is how has the study of projectile motion been important? So that's something I want you to think about as well. Why would we even care about projectile motion? Okay, now projectile motion is two-dimensional motion, as I said, and in dimensions we have a way of talking about that. And the way we do it is we often refer to the horizontal as the x direction and the vertical as the y direction. So we say that there's a horizontal component and a vertical component to two-dimensional motion. Two-dimensional motion that is going through the air anyway, a projectile that isn't just going straight up or straight down. And the path that they're going to take here as they fly through the air is called a trajectory, and we talk about the distance that it lands away, the horizontal distance as being the range. So a few vocabulary words about projectile motion. And there we go, there's a picture of a projectile. How has that been important in history? Okay, so there are two types of problems that I'm going to talk about with and talk you through today. And the first is a horizontally launched projectile. And the idea of a horizontally launched projectile, if it's going to be in two dimensions, then there is going to be a height that it's launched from, and we're going to be able to launch it horizontally from that height. So there is the trajectory of the horizontally launched projectile. So we'll start making calculations with those pretty soon. So we could talk again about the idea of here, the range of the projectile and the height that it's launched from. There's lots of examples of this, and we'll do some in class as well. Okay, so first let's talk about things that are going to be true for every one of these problems that you solve. So we're going to distinguish between what's going on horizontally and what's going on vertically. So horizontally, or in the x direction, we're going to have no acceleration. Now this isn't exactly true in real life because there would be wind resistance, air resistance, so all kinds of things would be taken into account in a real life situation, but we're going to build it up from the idea that there's no acceleration in the horizontal direction. And because of that, we're going to be able to see that the speed horizontally is going to be constant. And that means that if we're calculating the range, then the distance will be that constant speed multiplied by the time. And that's true for all of these horizontally launched problems. Okay, vertically, what's always going to be true? Well, for one thing, the acceleration is 9.8 meters per second squared. That's gravity. So we have an acceleration vertically of 9.8 meters per second squared. Also, since we launched horizontally, the initial velocity in the vertical direction was 0 meters per second. And that means we can always boil down the height formula to d is equal to 4.9 t squared. And this is taking our equation d is equal to vit plus 1/2 at squared and boiling it down because vit is going to be 0 since vi is 0 and 1/2 of 9.8 is 4.9. So that'll give you the height that the projectiles were launched from. And here's a little diagram showing what that motion looks like and just the idea of the different components of the flight. All of the equations that we've been using so far are good equations to continue to use, but you can't combine the horizontal and vertical in one calculation. You have to keep those separated. Okay, so the initial velocity of one of these things is entirely in the horizontal direction. So if you're ever asked for the initial velocity of a horizontally launched projectile, you'll be looking in the horizontal direction. That's the initial velocity. And as the projectile is falling, the velocity becomes a combination of the two. And for that, you would have to use a little trigonometry that we'll also discuss later in this slideshow. Okay, so here is an example. We have an example of a soccer ball kicked horizontally. There's the speed and there's the time. So this is a typically worded horizontally launched problem. And here I'm asking for the range of the soccer ball, and I'll also be asking for the height that it was launched for. I'm going to give the answers here so you'll know if you're on the right track when you try to solve them. The range of the soccer ball becomes 200 meters, and the height that it was launched from was 123 meters. I rounded that up from 122.5. But why don't you give that a try, see if it works out for you as it did for me, and when you come back I'll talk about the solution a little bit. Okay, well, welcome back, and here we have the solution for this problem. Okay, the first thing that I'm showing over here is the splitting it into the horizontal and verticals. As with every problem since the beginning of the year, the good first step is to identify the information that you have. And now it becomes a matter of splitting it into what's going on horizontally and vertically. So in the horizontal direction, we were told in the problem that the initial velocity was 40 meters per second. So in the x or horizontal direction, the speed is always going to be 40 meters per second. No acceleration there. And I'm also including the time, because here, and it's worth noting, the time in the horizontal direction and the time in the vertical direction are the same. It's traveling horizontally for the same amount of time as it's traveling vertically. So if I look at the y, or the vertical direction, here I'm indicating that its initial velocity was 0, and that its acceleration was 9.8 due to gravity, and there I've listed the time. These are the things I know particular to this problem before I start trying any solution. Now when I do try a solution, I can go ahead and solve for the range that was asked for in part A. D is equal to Vt, we know. The speed never changes in the horizontal direction, so this distance is equal to that speed multiplied by that time, and that's how I got the 200 meters. Now in the vertical direction, I started off with the initial velocity, the acceleration, and the time, and that gave me enough information to solve for the distance in the y direction, which we would also call the height. So here it is, the setup, and there you go. That's how I got my answers. I hope you had some success. If this still raises questions for you, then we can discuss them in class, certainly. Here's, okay, so I guess that's the idea of that first problem. All right, very good. Like I said, I hope that that was helpful. So now I'm going to ask another question of you here with the slideshow, and that is, or I'm going to tell you something that I've already said, the horizontal and vertical components act independently of each other. So the overall motion is going to be a combination of both of those things, but they do act independently of each other. So here's an old classic physics question that had me scratching my head when they first presented it to me, and that's the idea of bullets being fired. And that's part of the ballistic study, and that's a good example of projectile motion. It kind of goes back to that question at the beginning, why that might be important. But this one had me scratching my head, as I said. One bullet is fired, horizontally, and another is dropped at the same time from the same height. So they hit the ground. And which one hits the ground first? Well, how about it? What do you think on this one? Is it the one that's fired horizontally? Is it the one that's dropped? And it's a bit of a trick question because they both hit the ground at the same time. Gravity doesn't care much one way or the other, and vertically it would be the same pull and the same distance, so it would be the same time. Interesting, like I said, had me scratching my head when it was first presented to me. Okay, so here's another kind of projectile motion common to these physics problems, so we'll tackle this one next. This is one where the projectile is fired, where it launches and lands at the same height. So that's a particular kind of projectile, but a useful one for talking about these concepts. All right, now how about it? This is like a projectile that's being launched at an angle. It's going up and it's coming back down. This was a daredevil stunt motorcyclist, Evel Knievel, from some years ago. But what are the factors that are going to affect the range and the height of the motorcycle? So something to think about. Now, if you remind me in class, I'll recount a motorcycle story and we can talk about these factors. So I have a pretty good motorcycle story. At least I think it's a pretty good story. But you can ask me about that in class. Okay, so how about this? If you are firing something, which angle is going to give the farthest range? Right? So here is a diagram that kind of shows you. 45 degrees will give you the maximum range. Anything over 45 degrees, it might go high, but it's not going to go too far. And anything that's under 45 degrees isn't going to go as high, and it's not going to go as far. So 45 right in the middle gives you the maximum range. 45 degrees. Okay, and speaking of angles, it's time we talked about a little trigonometry. And this is stuff that you're already probably familiar with, the old SOHCAHTOA. So we're doing right angle trigonometry, and we deal with the opposite side of the angle, the adjacent, and the hypotenuse. And the hypotenuse, of course, is opposite the 90-degree angle. All right, so here's our SOHCAHTOA. We know what the sine is, we know what the cosine is, and we also know what the tangent is. So we're going to be, concerned with finding these things. So we are in degree mode on our calculators. We want to be careful not to be in radian mode. So if I were to ask what the sine of 30 degrees is, we should all be able to plug it into the calculators and get 0.5 as an answer. We should agree with that. And that just means that if the hypotenuse is 1 unit long, then for an angle of 30 degrees, the opposite side will be a half of that. And that's really what the opposite and the adjacent and the sine and the cosine are involved in. It's a ratio of each side to the hypotenuse if it was 1, if it was just 1 length long. Okay, another useful thing is finding the angle by knowing what the sine, cosine, or tangent is, and that's the inverse sine, cosine, and tangent. And if we feed in what the sine, cosine, or tangent is, we should be able to find out what the angle is. It's the reverse, the inverse. So what is the inverse sine of 0.5? Well, as we would expect, it is 30 degrees. So that's about the extent of the right triangle trigonometry that we're going to be using for projectile motion. Okay, so we're also familiar here with the idea, I think, of the Pythagorean theorem, and that's the c squared is equal to a squared plus b squared, and that's another one that we're going to find useful with right triangles in physics. Okay, so this is the kind of projectile that's launched and lands at the same height. It is going to have a very particular trajectory to it. And once again, I want to give you things that are going to always be true for these problems in the horizontal and vertical directions. So in the horizontal or x direction, the initial velocity is going to be the overall initial velocity times the cosine of the angle. That's the right triangle trigonometry there. And in the y direction, since the y is opposite the velocity, it's going to be multiplied by the sine of the angle. And if we know the cosine and we know the length of the hypotenuse, that's how we're getting these horizontal and vertical components. Okay, once again in the horizontal direction the acceleration is 0, and in the vertical direction as we're going on the way up, the acceleration will be negative. And the velocity in the y direction will be 0 at the high point. So halfway through the trip, the velocity in the y direction will be 0. Okay, so that's the time to the high point, or the velocity in the y direction up to that point. And from this we can find out how much time it's going to take to the high point. And the way that we can do that is because we know if we jumble up v final is equal to v initial plus acceleration multiplied by time, that the time is going to be the initial velocity in the y direction divided by 9.8. And that'll always be true, and we'll show an example of that pretty soon. Okay, and again, this is the time to the highest point. Alright, so this should make some sense also. The time to the highest point is only half of the trip. So if you're looking for what's going on overall horizontally, The time in the x direction is 2 times that time in the y direction. And that means that the range, or the distance in the x direction, is going to be that velocity in the x direction times the time in the x direction. And that's always going to be true. And again, we'll do an example and show you exactly what I mean. Okay, so here's one. Projectile is launched from the ground at an angle of 30 degrees and a speed of 100 meters per second. So here I want to know the range, and I want to know how high it goes. So what is its range, and how high does it go? All right, well, why don't you give that a try, and when you come back, I'll show you how I got the answers if you weren't able to. My answers were 883 meters for the range, and for how high it goes, I got 128 meters. But give it a shot. When we come back, we can go over that. All right, well, welcome back. Here is my solution. Let's see how it worked out for you. Okay, well, first of all, I split it again into the horizontal and vertical components. And in order to find the horizontal component of the speed, I took that initial velocity and I multiplied it by the cosine of the angle. And since there's no acceleration in the x direction, I'm indicating there that the velocity in the x direction is 86.6 meters per second, indicating that it will not be changing during the flight. In the vertical direction, I'm using the trigonometry and the sine function to figure out how fast it was initially moving in the y direction. And it turns out it's 50 meters per second. Remember, the sine of 30 was 0.5, so half of 100 is 50 meters per second. My final velocity in the y direction is 0, but again, that's at the high point. So it's not the entire flight, but when it gets to the high point, the velocity in the y direction is 0, and the acceleration that caused that to happen was negative 9.8 meters per second squared. So now here, looks like it's a little elongated there. All right, well, the math is still good. Here I'm using the equation, v final is equal to v initial plus acceleration multiplied by time, to find out in the y direction. I'm in the vertical direction here, and I'm finding out the time that it took to get to its high point. So hopefully the math there makes sense. I'm just plugging in the variables that I identified in the first step. But if it's trouble, we can certainly talk about it in class. Next here, I'm solving for part A. Remember, part A asked for the range. So I'm taking that velocity in the x direction that we calculated before, and I'm multiplying it by the time in the x direction. Here I'm taking that time in the y direction, the 5.1 seconds that I got, multiplying it by 2 to say that the entire trip was 10.2 seconds. And using d is equal to vt and that information, that's how I calculated the range. Certainly something we could talk about in class. Then I was wanting to know the height. And there's a couple of different options I have to find that out. Here's one of them. What I did is in the y direction, I found the average velocity in the y direction, and I multiplied it by the time it took to get to that height. And I found out that it was 127.5 meters. And if I put it all together, as I might in solving a problem like this is what all the pieces look like together. But that's how I got there, and I hope that that is useful to you. I certainly hope it will. But these things can be confusing, so if you're having questions with that, please bring your questions to class. And that's about it for this presentation, and that'll get us started on projectile motion. And thanks for watching, and I look forward to seeing you back in the class.